Good morning, good afternoon, or good evening, and welcome to the AVS eTalk series. Today's talk is Changing the Sun, Quantum Cutting Materials to Increase the Efficiencies and Lifetimes of Silicon Solar Cells with E-Ray Idle. We will be going through a few introductory slides here before we change over to letting E-Ray begin his presentation, so bear with me. Let's see, we do want to thank our sponsor, Hayden Analytical Instruments for Advanced Science, for sponsoring this eTalk. And when you logged in, you'll have noticed that you're automatically muted. Please be sure your volume is up and that your screen is in full view. This will be a 1-hour presentation, no breaks, but we will have Q&A at the end of the presentation. So be ready to type in your questions, and you can do that at the bottom of your screen. There should be a Q&A option. We'd prefer that questions come into that feature. So please feel free to type them in at any time during the presentation, and we'll cover those towards the end. We do have a couple of disclaimers and a copyright notice here. We believe all this is to be reliable and true information, and the material contained in this eTalk was copied with the permission of the author and instructor of the notes, and so on. So please be sure to note this information here. We do have an upcoming eTalk in September on heterogeneous integration for mmWave wireless communication systems. If you have an idea for an eTalk, we're welcome for more suggestions. Please contact Matthew Jordan. They are typically 1 hour in time and free to attend. So we try to keep the subjects broad enough to target our AVS community. So feel free to bring up an idea for us. Also, we usually have some webinars. We will be working on some for later this year. If you have an idea for a webinar, these are typically half day with a nominal fee associated with them. Our contact for subjects is Dave Adams. Also, we have an online international one tweet challenge. This is a challenge from our professional leadership committee, chapters, groups, and divisions committee via Twitter. The event dates are July 18th through 19th. You can check this out online, and registration is open. We also have AVS short courses. Right now, we're finishing up a program in New Mexico, and we're planning some for the fall through AVS National, and some of our chapters are also looking to put together some programs. If you have a course you're interested in, please complete our courses by request. If your company has a group of employees in need of training, we also provide on-site or online training options. You can check that out. Our short course catalog is available online, or you can contact me at heather@avs.org. And we have some upcoming technical meetings. 2 this month are the Frontiers of Characterization and Metrology for Nanoelectronics, June 20th through 23rd in Monterey. Atomic layer deposition with a workshop on atomic layer etching, June 26th through 29th. Our 5th U.S. gallium oxide workshop in August. NAMBY 2022 in September in Delaware. SIMS 23 also in September in Minneapolis, and our international symposium coming up November 6th through 11th. This will be in Pittsburgh, Pennsylvania. And rounding out the year is PAC-SURF 2022 in Waikoloa, Hawaii in December. All these can be found on the AVS website. And if you're not currently a member, we encourage AVS membership to expand your network, enhance your scientific and professional knowledge, gives you an opportunity to develop and practice your leadership skills, and gives you discounts on various events, hotels, insurance, and more. You can go to avs.org to find out more. If you're a student, this is a great time to find out about student membership, student chapters, career services, and ways to get involved. And finally, at the end of today's evaluation, please complete the online evaluation form that will also be emailed to you. And at this time, I'd like to welcome E-Ray Idle. He's going to present our eTalk on Changing the Sun, Quantum Cutting Materials to Increase the Efficiencies and Lifetimes of Silicon Solar Cells. E-Ray, if you'd like to share your screen and begin, we're ready for you. And again,
I hope everybody can see that. And
presentation mode for us.
Great. Let me grab my laser pointer here, the virtual laser pointer. Well, thank you very much for having me for this eTalk. I'm going to talk about something that we've been working on for the last 3 years in the middle of COVID. My students, Min Tran and Ivor Cleveland, have been working on it. And you may know that I moved from University of Minnesota to NYU, and in the middle of COVID, they set up the lab from scratch and did all the things that I'm going to talk about to you. There's more. I picked some sample results, and I want to take some time to set up the problem and why we're working on this. Min and Ivor are fourth-year students, and they will be looking for jobs come next spring. So all of this is their work, and I highly recommend both of them. So before I go on, I want to tell you a little bit about where we are. Tandon School of Engineering is the engineering school of NYU, and NYU is all over the place in New York. You may recognize this as the Manhattan Island, and NYU basically central is around the Washington Square. If you're familiar with it, Washington Square is actually a public park, but NYU has sort of claimed it as their quad. Tandon School of Engineering is on Brooklyn. You have to cross either the Brooklyn Bridge or the Manhattan Bridge to get to it. And sometimes I walk from Manhattan to Brooklyn. And when I do that and go across the bridge, this is my view. And I've done that plenty during COVID. Once you get to Brooklyn and to Tandon School of Engineering, this is what we look like. We're in several buildings. And this is our version of the Washington Park, the Myrtle Promenade. And this is the entrance to our school. When the day is over and I walk back to Manhattan to my apartment, if I time it just right with the sunset, this is my view on my commute. But I am to talk about photovoltaics and silicon solar cells in quantum cutting materials. First thing I would like to do is motivate why we're doing this. Department of Energy's Solar Energy Technologies Office, CETO, has set some aggressive goals. In fact, they recently changed that. This is a plot of levelized cost of electricity in cents per kilowatt hour, and for various different types of photovoltaics, residential, commercial, and utility. And you can see that since 2010, the cost has come down significantly. This is the 2020 cost, for example. Let's take a look at the utility, 4.6 cents, and that is competitive with other sources of energy. The goal is to take that down aggressively to 2 cents by 2030. So that's the goal. And this is CETO's plan on how to get there, what needs to be done. And so there are many different ways to work on to decrease the levelized cost of electricity. You can work on the module efficiency, improving lifetime, balance of system hardware and soft costs. What I'm going to talk to you about today has potential to have impact on both the efficiency as well as improving the lifetime. So the silicon solar cell efficiency, even though we've made a lot of strides in reducing the levelized cost of electricity, the silicon solar cell efficiency has actually stalled, and that has ramifications for the module efficiencies. They dominate the market, so it makes sense to work on silicon solar cells and technologies that might help silicon solar cells. The reason that it has stalled is because the efficiencies are approaching a fundamental limit called the Shockley-Quessier limit. And if you're not familiar with that limit, I will explain the nature of that. And in fact, what I'm going to describe to you is trying to surpass that natural limit. The Shockley-Quessier limit for solar cell efficiencies arises from the following fundamental considerations. Typically, you have a semiconductor that absorbs the light and creates electron hole pairs, and that's how one gets the current. If the incoming photon has energies less than the band gap energy of the semiconductor, it does not get absorbed. So you need at least the band gap energy to create an electron hole pair. If the light that comes in has energy greater than the band gap, then one creates hot electrons and hot holes. And when they relax very rapidly by colliding with the lattice atoms to the band edges, the extra energy that they had over and above the band gap energy gets lost as heat. Basically, more lattice vibrations are created, and that appears as temperature or heat in the solar cell. So there are two competing effects. If the band gap is too large, then one does not absorb enough of the light. If the band gap is too small, then a lot of energy is lost as heat as you create more hot electrons and hot holes. So those two competing effects sets up a maximum in the efficiency as a function of the band gap of the semiconductor. And that calculation was done back in 1961 by Shockley and Quessier. And it turns out that the maximum, the optimum, is around 1.1 to 1.3. And it's a pretty broad, forgiving maximum. And the crystalline silicon is right smack in the middle of it. So it's nature's gift to humankind. And you can see here various other semiconductors and technologies and where they sit with respect to their own Shockley-Quessier limit. Those are the champion efficiencies. So crystalline silicon is somewhere around here at 25, 27%. And it's approaching the natural limit. So that amount of energy lost as heat is actually significant. So this plot shows the percent of incident light energy that ends up in various sources. So sitting at around 1.1 eV, let's say around silicon band gap, here's the usable electric power. Here's the amount of photons or energy that we throw away because we can't absorb it. It's below the band gap. And here is that extra amount of energy that comes in from light absorbed to create hot electrons and hot holes. So it's significant. So it would make sense to try to recover some of that energy. Now, one way to surpass the Shockley-Quessier limit is tandem solar cells. So this is well known. What one tries to do is have multiple semiconductors with different band gaps, each observing different part of the spectrum and then adding to the current to increase the efficiency above that of the Shockley-Quessier limit. This here is the latest tandem solar cell that combines silicon with a newcomer, halide perovskite, to increase the solar cell efficiencies, and efficiencies ranging from 22% to 29.5% have been reported by using silicon and perovskites. Now, I will not go through about the role of each one of the layers, but one thing that you notice is that there are many, many layers. And so this adds to the complexity and the cost, but it's definitely an exciting prospect. So this is the first place I mentioned these halide perovskites. So unless if you're not familiar with it, I want to tell you about them a little bit. It's kind of difficult to read journals these days without coming across them. But halide perovskites came into picture back in 2010 when the solar cells based on halide perovskites were found to be surprisingly efficient, and efficiency has been increased significantly above that since then. Although their research goes back to 70s and 80s, even earlier. So they're compounds with formula ABX3, where A is a monovalent ion and B is a divalent ion, and X is a halide. And it's typically cubic, although the definition is relaxed. For perovskites, you can have orthorhombic and rhombohedral structures and other structures. But the characteristic structure is this BX6 octahedra. It is a octahedra of a metal and the halides, and they reside at the corners of a cube with the A ion halide in the center. Now, this definition of the halide perovskites have been more expanded, and basically these perovskites now, anything that has a structure made up of this octahedra, maybe in layered sheets, sometimes not even connected to each other, are called perovskites or perovskites derivative with some qualifiers, and I will talk about one of them shortly. So some examples that are cesium lead chloride, cesium lead iodide, for example, and you can mix the halides to make alloys of that. Okay. Now, I want to get back to the problem of surpassing the Shockley-Quessier limit. I want to give you an introduction to perovskites because they're used in tandem solar cells, but it's going to turn out to be important materials in what I'm going to talk about too. However, the approach that we're talking about is another way to surpass the Shockley-Quessier limit, and it is different than the tandem solar cell. So in this approach, one deposits a material on top of a silicon solar cell, and actually it doesn't have to be on top of the cell. It could be on top of a glass, then gets put onto the silicon solar cell to encapsulate, for example. And this magic material, the quantum cutting material, takes the blue photons and converts them to near infrared photons. So for every blue photon, one creates 2 near infrared photons. And if you have twice the bandgap energy, it would make sense to create photons with energies near the bandgap. So you have 1 photon creating 2 photons, and what gets absorbed are those photons. So here I show, for example, the spectral irradiance of sun. And you can see that here, and I left a lot of room here. So what we're going to do is take all the UV and blue light here and convert them to near infrared photons at the band edge of the silicon, about 1.1 eV. It turns out that the material system that I'm going to talk about, the emission is at 1.24 EV, but it's very, very close. So this is what we're trying to do. Take all those photons and lump them into near infrared. And hence the sort of provocative title, Changing the Sun. So what we send into the solar cell is not this, but this, so that we avoid heat losses due to relaxation to the band edges. There are other benefits to taking the blue photons to the near infrared, and that has to do with the external quantum efficiency of the silicon solar cells, or any solar cell for that matter. So external quantum efficiency is the number of generated charge per number of incident photons. And here I show both the normalized spectral irradiance for the sun, as well as the external quantum efficiency of a typical silicon solar cell taken from this reference. And what happens is that in silicon solar cells, recombination near surfaces, because UV gets absorbed near the top of the solar cell, the external quantum efficiency is decreased in the UV and blue regions. So you can see here is that below 500, the external quantum efficiency is less than 70%, and for 400, it's even as low as 40, 30%. On the other hand, near the infrared, the external quantum efficiency is nearing 1. So taking all these photons and putting them over here also puts them in a place where the EQE is closer to 100% or 1. And so that's because the near infrared goes into the silicon, deep into the silicon, absorbing the bulk where the recombination is low, whereas UV is absorbed shallow near interfaces where the recombination is high. So there is more than one way to win. So you might ask, how much can you increase the efficiency? So just to recap, the current record silicon lab efficiency is 27%. The theoretical limit, Shockley-Quessier limit, is at 33%, which is right here. If you recalculate, so go back to the Shockley-Quessier limit, Quessier paper, and recalculate what is possible with a perfect quantum cutting material, one gets that to increase that theoretical limit to 41%. So that's significant. And this number is arguable, but something approaching 35% realistically is not out of the question. Perhaps more important, and this was pointed out to me, more important than efficiency is actually UV degradation and heating reduction that comes with taking all those UV and blue photons and putting them in the infrared. And that could improve degradation and improve module lifetime. And from the how to get to 2-cent levelized cost of energy plot that the CETO had, this also has a significant effect. So both of these will contribute to lowering of levelized cost of electricity. So is this possible? Are there materials? And this seems obvious so far. Why haven't we done this yet? And basically, we've been looking at this for 60 years. Dexter was the first to suggest this mechanism. But there has not been a candidate quantum cutting material. And this is the sort of the first time where we have some prospects of it. I see that there is a question in the Q&A. And I will take some questions if they're relevant during the talk, but maybe some of these others I will leave it to the end of the talk. Okay, so we've been looking at this materials for 60 years, and it turned out that in 2017, Song et al. In China serendipitously discovered the magic material. It happens to be a halide perovskite. This is actually not surprising to me, because if you look at the number of articles written on perovskites and what people are trying to do, trying many different things with perovskites, asking, here's this hot material, how can it be used? What are its applications? So they basically took all the lanthanides and doped them into cesium lead chloride and see what would happen trying to get them to emit, using them as energy transfer hosts. And they hit the jackpot with the ytterbium. And here is the I have to, I think, get out and get back in because it's not advancing.
Is it frozen?
Yeah.
Okay. Give you a second to refresh if needed. I'm going to give Ire a chance to reload his presentation in case it froze on him. If you have any questions, be sure to type them in the Q&A. And it looks like he's coming back.
And that presentation has. Okay, I'm going to try again.
Okay.
Okay, so this is the telltale sort of sign of quantum cutting. And here the photoluminescence quantum yield, that is how many infrared photons we got from each blue photon. We can give it as percent or fraction. So 2 from 1, it would be 200%. So here it is for different lanthanides, hovering at 30%, 40%, not so surprising, and it gets to ytterbium, and it's greater than 100%. And there are some good reasons why ytterbium is different than the others, but this is the first time basically that a viable material for quantum cutting was discovered. Mechanism is not understood, but there are hypotheses. And since that early work, the most work on this has been done by Gamelin's group at University of Washington. And in fact, they have a company called Blue Dot Photonics where they're trying to commercialize this. And I will talk about what are the barriers to commercializations. They happen to be actually also a collaborator. Now, the mechanism is not understood, but there are some hypotheses. So looking at this absorption here, this is the bandgap of cesium lead chloride. So the semiconductor material absorbs here, and the energy is transferred to ytterbium, and ytterbium emits there. So how does that happen? So the first step is to get the light to be absorbed to create an electron-hole pair. And we think then that electron-hole pair or electron gets trapped in a defect. And that defect is in close proximity of two ytterbium ions. And upon relaxation, it couples and transfers that energy to the ytterbium. So this is the band picture, the physicist view of how things happen. If you want a physical picture, this is what we imagine. So that's the infrared emission. So this is what we imagine. So here is, again, revisiting the perovskite structure. So this would be the cesium. These would be the lead atoms and the halide atoms. So here's the lead. And if I take out 3 lead atoms and have 3 vacancies, that is 6+ ions I have to replenish. I can put 2 ytterbium, ytterbium is 3+, into 2 of those, and the third one remains. So there is hypothesis that this is the defect, and it's a complex, it's a charge neutral complex. And when the electron hole pair, the exciton, is created, it eventually gets trapped here at this defect and then couples into the ytterbium, and that's what makes this efficient. Now, whether this is true or not is debatable, but there is evidence for that. So where are we? Where's the state of the art and challenges? So I set up the problem. I would like to now talk about some of the things that we're doing. So the work that I talked about, both the work from Song et al. And Gamelin's work, is based on nanocrystal dispersions, colloidal dispersions, and films made using solution processing. And they have achieved now close to 200% photoluminescence quantum yield. Making films using solution synthesis, however, proved problematic. One big thing is that it exhibits large sub-bandgap absorption, so it absorbs things that silicon would, you would like to get to silicon. That's one thing. And the solution synthesis is not necessarily very easily scalable with the synthesis techniques used for perovskites. There are all sorts of problems that has to do with solvent compatibility, the solubility of the precursors and things like that. So good old physical vapor deposition that us at AVS are very familiar with is emerging as an alternative preferred method to produce quantum cutting fields. So we've been working on this. PVD films do not yet reproducibly produce films with photoluminescence quantum yield as high as nanocrystals, 190%. But we don't think that's a fundamental limitations, because there are PVD reports of close to 190%, but they're not as robust as one would wish. We in our lab, and we know from others, consistently get things approaching 70% with cesium lead chloride. This is Ivor's work that we're about to submit. The other problem is that lead is toxic. So one asks, are there other quantum cutting materials without lead? And that's what I'm going to talk about mostly today. And there are certainly gaps in our fundamental understanding of what makes ytterbium-doped cesium lead halides work. And it makes sense to look at other materials and see how they work and try to learn from that. So we do what I am calling reactive physical vapor deposition, because this is not the old physical vapor deposition where you have, just metals and atoms evaporated and then condensing on the substrate. But we evaporate precursors that upon landing on the substrate and condensing, they actually also react. And that reaction depends on substrate temperature and things like this. So I'm calling it reactive physical vapor deposition. So we do ours in a glove box system that is shown here. And we have 6 sources, 4 radioactive and 2 regular. And then we have quartz crystal microbalances, which we use for each one of the sources to actively control the deposition rate, because stoichiometric control is essential. We have a combinatorial mask that allows us to do high throughput synthesis. We typically work with 3x3 or 4x4 samples. So in a given deposition, we'll do 16 identical samples or 9 identical samples or 3 identical samples that may be annealed at different temperatures. We might put a gradient of composition and things like that. And our mask looks something like this. And we have just started playing around with actually putting in continuous combinatorial gradients to make libraries of different compositions. We just started doing that. The sources that I'm going to talk about, we have many, we have all the metal chlorides and bromides in this chamber. I'm going to talk about cesium chlorides and bromides, lead chlorides and bromides. Actually, I'm not going to talk about that much, but silver and bismuth compounds in a minute. There are advantages. Combinatorial synthesis, it's solvent-free. Stoichiometric control, we have very good stoichiometric control with most of our precursors, except those that are highly volatile. Reproducibility is excellent, and we make uniform films and intentionally non-uniform gradient films so that we can look at combinatorial libraries. And here is the early group. This is Ivor, who works on the cesium lead chloride material, and Min works on the alternative with Ivor on the new material that I'm going to talk about. Okay, so let me first answer the question of, are there other lead-free quantum cutting materials? And so if one thinks about cesium lead bromide, with the bromide atoms on the corner, lead in the center, and cesium in the center of the cube. And if I double that unit cell, here I show actually 4 of them. And then think of taking that 2 of the lead, that's 4+, and then hetero substitute with silver, which is a monovalent, and a bismuth trivalent ion. So every other octahedra is going to have either a silver or a bismuth, so that we have the charges compensated. So this color scheme of purple, gray, take your pick, is meant to depict the alternating silver and bismuth. So the compound that we're talking about, this called a double perovskite, because it comes from this derivative by doubling the unit cell. And we're going to do ytterbium doping, and ytterbium can substitute into either the bismuth or the silver. If it does substitute into the silver, it might have to form defects as well to keep the vicinity charge neutrality, whereas it's an isovalent substitution on the bismuth. So I will talk about this material. So some specifics about how we do the deposition. We do sequential deposition in the following way. We deposit the first layer, co-deposit silver bromide, bismuth bromide, and ytterbium bromide. And then we deposit a cesium bromide each 30 minutes. So it is layered. And then we anneal that film at 300 degrees centigrade for 1 hour. Using combinatorial methods, we use the temperature and the time, and this happens to be the optimum for reasons I will tell in a minute. The challenge with this one is that bismuth bromide is volatile. It begins evaporating at 60 degrees centigrade. So if you have the substrate temperature at anything above 60 degrees centigrade, not all bismuth bromide landing will actually remain there before reacting. It might actually re-evaporate. So for this reason, we explored different substrate control schemes. The evaporation rates of precursors are, depending on what we want to do, range, just to give you a feel, from 0.03 for ytterbium bromide, where we're trying to dope at low concentrations, to 1.8 angstroms per second for excess bismuth bromide. We typically use stoichiometric molar ratios, but we explored excess bismuth bromide with this compound as well. And film thicknesses, we're looking at a few hundred nanometers, and all the ones that I'm going to talk about are about 500 nanometers. So the first thing to establish is that when you do this, the target compound forms and ytterbium substitutes for either silver or bismuth. So here I show SEMs of two different scales, the films that one gets. They are polycrystalline, and depending on what you might call a grain, they're a few hundred nanometers up to micron in size. The X-ray diffraction matches cubic cesium-2 silver bismuth bromide 6. So here is the simulated structure, and this is the X-ray diffraction pattern of various ytterbium doping levels. And if you look at the peaks shift very subtly, but we establish the substitution of ytterbium by using Raman spectroscopy, actually, not necessarily X-ray diffraction. We detect impurity phases when the ytterbium concentration is in excess of 10%. So here, for example, we have excess silver bromide. And we think that's because ytterbium substituting to silver might kick out some silver bromide. That's how we get the silver bromide. EDS is consistent with ytterbium doped 2116 stoichiometry. Raman spectra is what shows the substitution of ytterbium for silver or bismuth. And you see here is the metal bromide peak shifts to higher wave numbers with increasing ytterbium concentration. Ytterbium is smaller than both bismuth and silver. So in the octahedra results in lattice compression, and that lattice compression is expected to give Raman shift. And so this data is actually pretty clear, the shift, and confirms that ytterbium incorporation into the octahedra. We can't tell whether it's going into the silver or the bismuth yet, but we have some data to suggest that we might be able to, but we haven't yet got to the bottom of that yet. So here are the optical properties, and I will show you in a minute that it does emit in the near infrared with up to 80% photoluminescence quantum yield, and lately we've gotten up to 95% photoluminescence quantum yield. Basically, the threshold to get any efficiency improvement is about 70% for silicon. But to be commercially viable and competitive, we really would like to get to at least about 130%, and definitely closer to 200% as possible. So what is shown here is the absorbance of this material, which I would refer to as a 2116. And you see there's an exciton peak here. And when we excite with anything under here, come in with, for example, 360 nanometers, etc., we get the material to emit where exactly it's supposed to emit. It's about 1,000 nanometers, corresponding to about 1.25 electron volts, and it corresponds to the ytterbium transition. So basically, this blue light ends up converting to the near infrared. What is plotted here is also the excitation spectrum. So if I sit on top of this emission and then change the excitation wavelength, the photoluminescence quantum yield basically remains about constant. And when you try to excite below the bandgap of the material, you don't get photoluminescence, which is what you would expect. Effect of ytterbium concentration on photoluminescence quantum yield looks something like this. Here we show also data for different annealing and different annealing times. The films annealed at 250 degrees centigrade tend to be unstable in air. So when we take it out in the air and let it sit around, its photoluminescence quantum yield changes. So some of these decreases are due to how long we waited to make the measurements, etc. But when you do the annealing at 300 degrees centigrade, we get high photoluminescence quantum yield. It's constant. I'll show you it's stable in air. It decreases above 8%, and this is consistent with impurity phases appearing when it's greater than 8% ytterbium. There's also a phenomenon that I don't have time talking about called concentration quenching. Basically, you can't have too many ytterbiums, and they exchange energy to lead the energy to a non-radiative defect, which then decreases the photoluminescence quantum yield. We've done different temperatures of annealing. 300 degrees centigrade is optimum annealing because it decomposes at higher annealing temperatures. And when we go below, photoluminescence quantum yield is not really stable. I have just a little bit of time to talk about importance of the temperature and bismuth bromide flux. So remember now, we've done a lot of experiments because we can do combinatorial. So I'm telling you what works and why we think it works. Some of these schemes we arrived at with a combination of rational thought as well as happy accidents, which I'm happy to talk about. But just to remind you, we're depositing bismuth bromide, silver bromide, and ytterbium bromide in one layer, and then cesium bromide in another layer. So it turns out that if you keep the substrate temperature at 30 degrees, 50 degrees, or 48 degrees, and around 75 degrees, you get 47%, 45%, 48% photoluminescence quantum yield. So it doesn't change very much, and it's definitely not at the high level that I was showing you. If, on the other hand, you ramp the temperature from 30 degrees to some upper temperature, then you get to 60% and 62%. Note that these temperatures, you're passing these temperatures along the way in the ramp. So ramp is doing something. It's not the temperature that you end up in. So it is doing something. And what we think is happening is that there is competition between the bismuth bromide re-evaporation and having high enough temperatures for the precursors to react. So we tested that hypothesis by actually bringing in excess bismuth bromide using one of these ramps. So starting with stoichiometric bismuth bromide arriving at the surface at 60%, so it's that experiment. We increases the bismuth bromide, and this is how you get to 80% by having excess bismuth bromide. So we're sure that the bismuth bromide flux and loss is important. And it's all about balancing the reaction with the bismuth bromide tendency to leave at higher temperatures. When you look at the films that are deposited at low temperature, you do find that you find the target material, the cesium, silver, bismuth bromide, but you also find still unreacted precursors. So the reaction is not complete and the annealing is needed. Something about stability. So films annealed at 300 degrees centigrade 1 hour are stable under ambient conditions and retains greater than 93% of its photoluminescence quantum yield. This is one of our champion after something like 70 days. And this is the same material, same data that I just showed you, the dependence of photoluminescence quantum yield on bismuth bromide, with all the data points taken after 2 months. And so you see that they're pretty consistently remaining high, and so it's they're stable in air. So I talked about very high photoluminescence quantum yield. So the question is this quantum cutting? Okay, so unfortunately, I'm here to tell you that we have data to show that the emission mechanism in this particular case is not quantum cutting. At least there is a mechanism that is not quantum cutting contributing to the photoluminescence quantum yield. There could be still quantum cutting happening in the material, but most of it is quantum cutting. And the reason for this is that below 500 nanometers, we have still photoluminescence quantum yield or emission from the infrared. And the significance of that is that to have two of the ytterbium excited at once by quantum cutting, you need 2.5 electron volts, and that's that threshold. And what I'm showing you here is photoluminescence quantum yield beyond that, and then going to zero at the band gap. So definitively, we can say that there is sort of garden variety down conversion, not quantum cutting happening. So what are we doing to that end? We are exploring. So one thing is that the band gap of that material is actually too low. We would like the optimum for the cesium lead chloride bromide happens to be around 490 nanometers, or exactly 2.5 electron volts. So we're shifting the band gap of our material, the lead-free material, by going from bromine and incorporating chlorine. And this data shows that by basically taking and systematically varying the chlorine, we're able to shift the band gap. There is also substitution that you can do for the bismuth, for example, indium, antimony, or gallium. And I have my students also working on that. Yukun is working on indium and antimony, and Min is working on incorporating chlorine. So I'd like to summarize and conclude. I think efficient quantum cutting is a viable way to improve silicon solar cell efficiencies beyond the Kaiser limit. Physical vapor deposition, I think everybody is looking, almost interested in this phenomena, is looking into physical vapor deposition for depositing all the candidates for quantum cutting. So this material has already been shown to have quantum cutting, and we're working on that. We can do ytterbium doping, and I shared with you this one compound. I think double perovskites as a lead-free host material for ytterbium doping, and they may exhibit quantum cutting, even though my last slide showed you that with that particular material, there was something beyond quantum cutting that was happening. And the fact remains that ytterbium doped cesium, silver, bismuth, bromide is the highest, and we got it now to 95%. I didn't talk about much, but the data that included the non-quantum cutting result also included new result with 95% photoluminescence quantum yield. And so that is above the threshold to get any efficiency improvement, certainly. It's not as high as what we wished, knowing what we can do with cesium lead chloride, but we have some directions that we're pursuing to push the quantum cutting. So here's my contact information. I'm also on LinkedIn, and I tweet and on LinkedIn, put a lot of Journal of Vacuum Science and Technology material. I am the editor-in-chief of Journal of Vacuum Science and Technology. So it's something that you should, a journal that you should consider for your own results. So I will stop here, and
if you want to leave your closing screen up, there's questions already in the Q&A for you, E-Ray.
Okay, all right. Just
so we'll go ahead and do it that way. Sorry about that.
I might
Since
have to
the
go
questions
back.
were already there.
I might have to go back and do this.
Okay, no problem. I do want to thank everybody for typing in their questions. Feel free to type in more. We're going to let E-Ray go ahead and do the Q&A, and then I will follow with some closing slides. I was going to do closing slides first, but since there's already questions in there for him, we'll go ahead and let him address
so I'm going to take, so do the monovalent cations always occupy the octahedral interstices in the perovskite. So the monovalent ions is in the cube octahedron. It's not in the octahedra. The 2+ ions in the classic perovskite are in the octahedra center. In the double perovskites, monovalent, trivalent do also occupy the octahedra. If the blue to near infrared conversion ratio were different, would that change the Shockley-Quessier limit. Yes, I mean, so basically you need to get to the 200% well, anything above 100% will allow you to surpass Shockley-Quessier limit. What if the TB3 plus ytterbium 3 plus couple was used instead of the double couple? One can try. That's not something I would try, because one of the things that I talked about ytterbium 3 plus is that it has only 2 levels. So there is only one transition that the energy can couple to. When you go down to the other lanthanides, the energy diagram is a zoo. So you'll couple the energy into various different emissions. If one is trying to get broadband emission, that's great, but that's for more like light emitting diodes and light emission. For this particular application, I think ytterbium is it. So those were all by me here. Nejmi says, thank you, Ire, great talk, thought-provoking. Any promising efficiency value reported using quantum cutting that might be represented in the NREL chart you mentioned about a startup company? So yes, Blue Dot Photonics are making silicon solar cells. I do not know if they have any confirmed efficiencies that might be represented on the NREL chart. I'm pretty sure they might look into it. It's a new company. There is not NREL certified, but there is a paper from China where they used it on silicon solar cells and showed, compared to without the layer, increased efficiency, but not on a champion cell. So, sorry, complicated answer, but I think it is viable, but nothing on the NREL chart yet.
All righty, thank you very much. I'm going to give everybody a few more minutes to type in some questions. I'm going to go ahead and share some closing slides. That way, if anybody has any final questions, we still have a few more minutes to go. So one moment, please, and I'll share my slides. All righty. All right, so Ire, thank you again for preparing and presenting our AVS e-talk on changing the sun, quantum cutting materials to increase the efficiencies and lifetimes of silicon solar cells. We appreciate you putting all that together and being available to share with our audience today. I do want to also thank Hayden Analytical for being an AVS e-talk series sponsor, so thank you to Hayden Analytical. We do want to note we have some upcoming e-talks, webinars, short courses. The next e-talk is scheduled for September 28th on heterogeneous integration for mmWaves wireless communication systems. So if that's something you're interested in, it's 1 hour, it's free, and registration is open. So give that a check. And also, if you have an idea for a future AVS e-talk, please feel free to contact Matthew Jordan. He is working to schedule e-talks. So we'd like some subjects. If you have one, they're 1 hour and free. So please check those out. Webinars, we will plan to have some hopefully later this year as well. But if you have an idea for that, you can contact Dave Adams. These are typically a half-day online session with a nominal fee, and we post those on our website. And so we'd like to hear from you if you have any subjects you'd like to know about. And once again, we have the AVS 2022 International One Tweet Challenge. This is being promoted by our chapters, divisions, and groups. And we'd like to have some interaction going on here. So if you have something you'd like to tweet about and want to participate, you can find more details on that. And registration is open. So check that out online. And we are planning some short courses for the fall, but right now we'll take some requests to put together our programs, either for our national offering, planning for September, or even our chapters are looking for requests from you. So check out the courses by request. If you have any online training that your company is in need of, check out our short course catalog and get in touch with us. We have some technical meetings coming up, a couple of them right around the corner in June, one in Monterey on frontiers of characterization and metrology for nanoelectronics, our ALD, ALE in Ghent, Belgium, GOX in Washington, DC, that's gallium oxide workshop, NAMBY, SIMS, AVS 68th International Symposium and PAC Surf are all rounding out our fall months, so check those out. Our events calendar has all the information for these events. Registrations are coming to be open, so check those out. And if you're not a member, we always encourage that. This is a great way to expand your knowledge network, enhance your knowledge, opportunities for leadership and discounts. And I'm going to continue to move through here. You can find out everything you want to know about AVS on the avs.org website. Membership will give you discounts on short courses, webinars, access to our technical library, publications, and journals. We have a YouTube channel. Students are also welcome to join and become part of student chapters and get involved with AVS. And there's an online evaluation in the chat. I posted the link to that, but I will also email it to you in case you miss it. And if there are any more questions for E-Ray, let's take a look at the Q&A and see if there are any additional questions for you, E-Ray, or not.
I just want to say that, we have several papers on this. One is just coming out in Materials Horizon, just saying the proofs impact. And if you need any more information, you can just email me and contact me.
Wonderful. And thank you again to everybody for participating. Appreciate your time. E-Ray, thank you again. And we hope to have another e-talk series scheduled. So keep us in mind and check out our events calendar, everyone. And thank you to all.